This video will cover an introduction to mass spectrometry, how to determine the empirical formula of a compound given mass spectrometry information. If we think back to the problem of determining structure from an IR, once again, if we were given just the IR and we were told to determine a Lewis structure for that compound, we would be in a bit of a bind. We could maybe identify it as a saturated hydrocarbon. Maybe we could even identify it as an ether, but all that would give us would be some structural features, not anything that we could build an implicit Lewis structure. As a minimum, if we were given the molecular weight of 88 from the mass spectrum, then we could probably deduce a possible empirical formula and maybe come to some conclusions about what the structure could be. But really, what we need is the empirical formula of the compound. And that can be deduced from looking at the mass spectrum a little bit closer. This really starts with the question of what is actually the molecular weight of a compound? Really? If we think about something simple, like methane, we've all been taught that we can add that up and there's 12 for a carbon and 1 for a hydrogen. That would get us from 16. But those masses, if you remember back, are really just the average of all the isotopes that are present. You've got to remember that there are, in fact, 2 separate isotopes of carbon. Carbon can come as a carbon-12, or carbon can come as a carbon-13. Both of those are present and unavoidable in nature. Out of 100 atoms of carbon, the natural isotopic abundance is 99 of them are going to be a carbon-12, and 1 out of 100 of all carbons is a carbon-13. That means if I took a statistical number of methane molecules and threw them into a mass spectrometer, I should have mostly things that weigh 16. 99 out of 100 would be molecular weight 16. But as a naturally occurring isotope, 1 out of every 100 molecules of methane would actually weigh 17. So if we looked at the molecular weight of methane, if we looked at the mass spectrum, there should actually be 2 peaks, 1 at 16 and 1 at 17. Of course, the 1 at 16 is going to be really big, 99 times as big as the 1 at 17. If we normalized that spectrum and made the carbon-13 peak 100% of the spectrum, then that peak at 17 would be 1.1%, 1 over 99. In a mass spectrum of methane, the largest peak would be 16 because it's the most isotopically abundant isotope. But the peaks would occur both at 16 and at 17, with the peak at 17 being tiny, about 1.1% as big as the peak at 16. This same kind of process can be applied to something like ethane. C2H6. We could ask ourselves, what is the molecular weight of ethane? And again, if we just added that up, normally the mass of a carbon, we'd have 2 carbon 12s and 6 protons. We add that up, we get 30. But if we had 100 molecules of C2H6 and each molecule contained 2 carbons, that would mean there would be 200 carbon atoms in that mix. 100 carbon ethane molecules, therefore, would contain 198 carbon 12s, 99 out of 100, and 2 carbon 13s. 100 molecules of C2H6 sitting on a benchtop would have to contain 2 carbon 13 atoms simply by the statistical abundance of carbon 13s in nature. So if we have 100 molecules of ethane laying around, that means 198 of them are going to be C2H6 with all carbon 12s, but odds are 2 of them are going to have a carbon 13. And that's going to make a molecular weight of 31. So what's the molecular weight of ethane? The truth is 30 and 31. 30 most predominantly, 31 a little bit. If we looked at the mass spectrum then, we would see a peak representing those molecules of ethane that have just the carbon 12s at 30, and we'd see a little peak at 31, which would be 2 out of every 100 molecules. So there would be 2 of them and 98 again. In a normalized spectrum, that means the peak at 31 would be 2.2%. The odds of both of them showing up in the same molecule, so you'd have you got 100 molecules laying on the benchtop. The odds of both carbon 13s ending up in the exact same molecule, that's almost 0. So your odds of seeing a 32, that's probably not going to happen. Those 2 molecules will show up, those 2 atoms of carbon 13 probably show up in 2 different molecules, meaning 2 out of 100 molecules will weigh 31, 2.2%. We can use that information to start identifying how many carbons are in a molecule. If we look really close at the molecular weight region of a mass spectrum, we can see that there's additional information that we can tease out. For example, if we look closely at this mass spectrum, we see that the molecular weight is probably 78. Notice that the fragments are predominantly odd. So if we have a molecular weight of 78, then we can see these little peaks showing up at 79 and 80. Let's focus on that one at 79. If we have a peak at 79, that might be occurring from an isotope of the carbons that exist in the molecule. As a review, 1 carbon made a carbon-13 peak of 1.1%. 2 carbons made a carbon-13 peak of 2.2%. In this molecule, the carbon-13 peak is about 6.6%. Compared to the peak at 78. It's not going to take much to conclude that the only way to create a C13 peak at M plus 1 due to the isotopes of carbon is if there's 6 carbons in this molecule. 6 carbons in this molecule would add up to 72 AMUs. Logically, this molecule can only have the empirical formula of C6H6. We can look at another molecule. Here we have a molecule in which the molecular weight of the entire molecule is probably 58. Notice again, odd fragments predominantly. If we look, 58 has a percent composition of 12, and its C13 is only 0.5%. Off the top of our heads, we might say 0.5% is not enough even for a normal carbon isotope. But let's look at this a little closer. We can even look at the isotopes of fragments. For example, we might know that the isotope of this fragment at mass 43 is 3.3%. That means that this fragment probably contains 3 carbons. But we want to know how many exist within that intact molecule. Remember that the isotope is the percentage of the peak that made it. That means that 0.5% down there in the noise is created by this thing that is only 12% big when we normalize the entire spectrum. So really, all of this information is just fragments. What we really want to know is how big is 59 compared to 58? What percentage is the C13 peak? If we look at that, the 59 peak is 0.5 the entire spectrum, and this is 12 of the entire spectrum. Relatively speaking, if we divide those two, we get about 0.042 or 4.2%. This peak at 59 is 4.2% as big as that is 58. That suggests that the peak at 58 has 4 carbons due to the C13 peak at 59. That makes this compound C4H10. Based on the C13 peak at 59. That makes sense. Then the fragment ion would be 15 AMUs later, or the loss of a methyl group, and make that C3H7. We can identify the empirical formula of the intact molecule, as well as the empirical formula of the fragments.